Hello and a warm welcome to our today's talk on cogeneration of heat and power in combination with thermal energy stores. You know probably that always my videos contain the process of the energy transition towards renewable energy generation. And then we could ask, why then a video, a talk on cogeneration? Nowadays most of cogeneration units still run with fossil energy systems like gas and coal. But nevertheless, cogeneration is a very efficient way to generate heat and power. And on the other side, cogeneration is compatible to the energy transition process because it also can be run by bioenergy or in future by synthetically generated natural gas, for example. So what is today's talk is, first we have an introduction on cogeneration. We look on the basic functionality of CHP units, the process of cogeneration, the operation modes for cogeneration units, and power to heat ratio and degree of freedom. Those terms we learn to know what it is. And then we look more to the role of energy storages, and here especially on thermal energy storages, because what we already have seen for the energy transition purpose, when we have a lot of power generated by sun and wind, we need energy storage. And what we can say is that thermal energy storage is by magnitudes cheaper than electrical storage systems. And when we can fulfill the task of energy storage on the thermal side and not on the electrical side, then we have gained a lot of economy in the transition process. So the reason why I'm standing here today, not in a normal suit, but here with the shirt of the football team here of Cologne, is that in the end we would like to highlight what dimensions we have when we want to store energy in a thermal way and how much we can supply by thermal storing. So, but first we start with cogeneration, with CHP units. And what is CHP, combined heat and power? The traditional way we see more on the right side here of the slide, and that is we have at home our heat generation system supplying the heat for our houses, buildings, industry. And on the other side we have somewhere far away located the power generation, also generating heat to produce power, but the heat there is wasted. And the overall system is a very inefficient one. And combined heat and power means, as we see here on the left side of the slide, is that we use the waste heat that is produced by power generation for heating purposes at our homes and also in industry. But to explain more in detail how combined heat and power and also district heating systems work, we first have a look on a video that by courtesy of Rhein Energie we are allowed here to show.
Today we want to reveal you something about the efficient use of energy, of which not only many customers of Rhein Energie have been profiting from for years, but also the climate. In our Cologne power plants, we use natural gas as fuel, and this not only generates electricity, but also district heat. The clever process is called cogeneration. We use the technology in our power stations, producing 50% electricity and up to 37% heat out of 100% used energy. Therefore, only 13% of the input energy is unused. In case of conventional power plants, which generate only electricity, around 60% of the input energy is lost. Wow, but how does a CHP work? We will show you this with an example of one of our combined cycle gas turbines, CCGT. By burning gas, the gas turbine drives a generator which produces electricity. The exhaust air from the turbine is several hundred degrees hot, which we use further. The hot air is passed into a boiler where it heats up thousands of pipes and evaporates the enclosed water. Here we showed the system a little bit simplified. The steam drives the steam turbine, which runs the generator. By doing this, we generated electricity for the second time. Part of the steam is dissipated and transfers its thermal energy to a hot water circuit via a heat exchanger. The heated water then flows through the underground district heating network to supply heat to households and companies. The water is cooled down after flowing through the network and comes back to the plant to be heated again. Is it clear so far? The so-called degree of utilization, which is the share of usable electricity and heat, can be up to 87% in a plant like Unit 2. From the 100% input energy, we produced 37% heat and 50% electricity, but that you already know. The electricity is fed into our electricity network, and the heat is supplied to our 4 district heating networks in Cologne. Now let's look at CO2 emission. In a conventional power plant, the emissions are very intense, while with this modern CCGT plant, we can save up to 500,000 tons per year. Of course, the Rhine Energy is expanding its use of renewable energy more and more. But for those cases when the wind does not blow and the sun does not shine, we provide our power plants for safe and reliable supply around the clock, 365 days a year.
Next, have a look on the operation modes of cogeneration units. And the first we consider is the heat-driven operation mode. And that's the one how most systems, at least in Germany, are operated. And that means that our CHP systems are primarily dimensioned to cover a heat requirement. And the generation of electrical energy is a secondary importance in this application. So surplus energy or electrical power, if not needed by the system operator, is then just fed directly to the public grid. And usually CHP systems, at least in former times, have been designed just to provide the maximum heat load, and therefore so-called peak boilers are also introduced in order to cover the peaks of the heat demand. That is the typical load curve, the heat load curve in a Central European application. And we see these white peaks here on the winter term at the beginning of the year and in the end of the year. And in between, in the summer months, we just see that flat bar that is just for the hot drinking water, the domestic hot water requirement. And traditionally, those systems had been designed to get a large number of full load hours just to cover this hot water demand in the summer months. And for the rest of the year, additional boilers have been used. When we put this graph in another order and in the magnitude of power required, then we see here that line with a high peak on the very left. So only a few hours per year we have a really high energy demand for the very, very cold days. And then this curve is decreasing towards the summer when we just have only the hot water demand. And when we look to the books on CHP units, they always make us believe we need something like 4,000 or 5,000 hours operation time of CHP units per year to being economic feasible. But that for sure needs to be changed when we go for the energy transition purpose. That we have smaller times, but with higher peaks, and the profit, the economic profit, needs to come then from the shorter times when we need the power, when there is no power from sun and wind, for example. The second way to operate a CHP system is the power-driven operation mode. And that is what we need in future and already is in place in some other countries. So that is strongly related to a CHP policy in different countries. And there the CHP system is primarily dimensioned to cover the electrical power requirements. And the generated heat depends then on the need of the electrical power, and should not be dimensioned to the maximum amount of the required heat. Otherwise, excess heat would be wasted in coolers and is not anymore used. In case the heating energy should not be enough, again, peak boilers can produce the excess or the needed energy there. To get a bit deeper in the material of combined heat and power, we have certain figures that we need to explain, and the first is the power to heat ratio. So we have a lot of technologies that can work as a combined heat and power technology, but this relation, electrical power divided by the thermal power, that is this power to heat ratio and differs from technology to technology. So for example, we have in steam turbines, whether we use back pressure turbine or extraction condensing turbines, is somehow between 0.3 and 0.5. Or you see a much more technologies here. When we go more to the diesel and gas engines, it is typically a factor of 0.5 for the smaller ones, and we go to big ship diesel engines, it can go up to a figure of 1, meaning we provide the same amount of energy for electrical energy and also for thermal energy. Another term is the so-called degree of freedom, and there we have systems having 1 degree of freedom, and that means that this power to heat ratio is always the same, it's a constant. But of course we can vary, we not need always to operate the system with nominal power, we can downgrade it in operation, but this relation between power and heat is always the same. And then we have systems that has 2 degrees of freedom, and that means we can even influence the relation between power and heat. And here on those graphs we have few examples of that. On the left side we have those systems having just 1 degree of freedom, and that is typically the motor-driven CHP units. It is gas turbines with no more features. But then on the right side we have this example with a 2 degree of freedom system, and there we see it's not just a straight line, there it's a field of operation. That means horizontally we have the electrical load and vertically the thermal load, and just by changing the ways how we generate electricity, what we use for example of the steam generation, we can influence the power to heat ratio. And here again we have some technology with the indication whether it is 1 degree of freedom or 2 degree of freedom, and all that is explained much better in the second video we have produced, where the different technologies are discussed and explained why we have in some technologies only 1 degree of freedom, in others we have 2 degrees of freedom.
The steam turbine. In the back pressure mode, the steam is produced by a boiler and is sent to the steam turbine. The steam is distributed to the high, medium, and low pressure parts of the turbine. The turbine drives a generator which produces electricity. The steam is condensed after passing the low pressure part of the turbine, and it will be used to supply a heat consumer with hot water. After this, the cooled water starts the steam production process again. A disadvantage of this process is that at least 1 heat consumer has to be connected. In the condensing mode, steam is produced and again is used by the turbine to drive a generator. However, here the steam is extracted early in a hotter stage, and only part of it goes back to the steam production process. The remaining part is used to produce district heat via a heat exchanger. The gas turbine. This is a gas turbine. It needs air and natural gas to operate. With this, it drives a generator which produces electricity. With the exhaust gas of the turbine, it is possible to heat a heat exchanger which supplies district heat. If one were to extend this system by returning the steam into the suction apparatus of the turbine, a so-called chain cycle would increase the performance of the turbine. Gas and steam turbine plant. This is again a gas turbine. it needs air and fuel like gas to operate. This way, it drives a generator which produces electricity. The exhaust gas is around 500 degrees Celsius, which causes the water flowing in a heat exchanger to evaporate. This steam is used to drive a steam turbine, which is also connected to a generator that produces electricity. After the hot steam passes through the condenser of the turbine, it heats a second heat exchanger which supplies hot water to the district heating network. This is a 4-stroke combustion engine. The engine burns air and fuel like gasoline or diesel and produces rotation. This way, a generator is driven. The generator produces electricity, and the water, which protects the engine from overheating, releases its thermal energy to a hot water circulation system via a heat exchanger. This is a fuel cell. It consists of a vessel, which an anode and a cathode, as well as a membrane, which separates two substances, hydrogen and oxygen. These substances cannot pass through the membrane. However, the oxygen proton passes through the membrane. Since the hydrogen wants to react with the oxygen, it separates into a hydrogen proton and into an electron. This electron flows from the anode to the cathode, producing electricity. The hydrogen protons and electrons react, generating hot water, since now there are a lot of them.
So on this slide here we have again those processes of CHP and some characteristic data. So we have in the first column we have again the power to heat ratio. In the center we have electrical efficiencies of typical units, and on the right column we have the overall efficiency. That's just for information. But let's come now to the more interesting thing when talking on the energy transition process, and that's the thermal energy stores that we attach to the CHP systems for the load balancing. And looking a bit on Europe, on the different strategies, how CHP is applied, and there we see a very different application of combined heat and power for electricity generation. And one could assume that in the colder countries in Scandinavia, CHP is used more than in the hotter countries in southern Europe. But as we see on this map, it's not the case. So we have, for example, Portugal has a quite high share of CHP used, and we have Norway with a very low CHP fraction. And the idols for CHP use is always Denmark and the Netherlands. They have a political way to implement CHP that led to shares of CHP that goes close or even above 50% of the generation. Here we see the same relation just in a bar diagram, with totally on top on the right side Denmark, followed by Netherlands, and then much lower many other countries, and among them also Germany. But let's discuss here now why it is so interesting having CHP as a source for control power that we need today and need in future when we run our system on wind and solar. And what we see here is the positive control power range a CHP unit can give. And that depends, for example, a lot on the outdoor temperature. So let's assume we have a CHP unit supplying the heat, and we have energy storage that at the moment is empty. And we have very cold temperatures. That is what you see on the very left side. Then CHP units operates almost with full power, with rated power, and what we can give in excess to power to the system is very small or close to nothing. But then on the third dimension of the diagram we see in a cold situation we can provide a small amount of control power a very long time, because we have a very long time then until the empty heat storage would be filled up. And then look to the other side when the temperatures are rising and it's more, let's say 10 degrees outdoor temperature, then we don't need any more the full power operation of our CHP units, and can, when there is power needed, electrical power, can increase the power provision by the difference of the actual power provision until up to the nominal power of the CHP unit. That means then we can provide a high control power, but the time is getting shorter because when we provide excess electricity, we provide excess heat, and the faster the thermal store would be filled up and is full and cannot take any more capacity to the system. For the negative control power, it's completely the opposite, and here we consider again a CHP unit together with a full heat storage. And that means when it's again very cold, which is again on the left side here, that means negative control power, we need to take away electric power. Of course, when it's cold and the CHP is in full operation, we can downsize the power provision by a high power. But then, of course, we can only do that a small time, because then we provide the heat load by the thermal store, and then, when it's very cold, the thermal store is discharged quite fast. And then it's the opposite. When it's getting hotter, the CHP only runs a few times, or it's only in a small power range. That means we only can decrease the power a bit. So we only provide control power in a low dimension. But then we can do that over a long time, because then it takes a long time until a fully charged heat storage is discharged. That's the way CHP and heat storage can accomplish the energy transition process, mainly based on solar and wind energy. The good thing is, when we have heat pumps, for example, with thermal store, it shows the complete opposite behavior. So, for example, showing the positive control power, we have said when it's warm, the CHP unit can provide high power, but only a short time. A heat pump would provide control power in a positive way by shutting down. That means when it's very cold, they can provide a high primary control power, but that only for a short term. And so they accomplish each other very well. And now we have some examples here of large heat storage units, and one of the most famous one is the one here in Theiss in Austria. And that formerly was an oil tank, an old oil tank, has a height of 30 meters, diameter of 50 meters, and has a capacity of 50,000 cubic meters. Or here in Germany, in Chemnitz, we have both. We have thermal stores and the cold store. On the left side we see 36 thermal stores, very high, very thin, in order that we have a good stratification of the heat here. And on the right side we see a cold storage for cold water, supplying a district cold system there. Or we have here again an example from Austria in Linz, a volume of 34,000 cubic meter, going up to temperatures of 97 degrees Celsius, having an investment cost of 4 million euro, a height of 65 meters, diameter of 25 or 27 meters, and an insulation thickness of almost half a meter. And here again example from Germany, from MVV Energy in Mannheim, and that has a height of 36 meters, a diameter of 40 meters, a volume of 45,000 cubic meters, and has a storage capacity of 1,500 megawatt hours of thermal energy. And to finish here, we would like to give a better impression, because it's always the question, how much energy can we store in a certain volume? And how long can we supply then a load, for example, a city like Cologne with that storage volume? And we have produced here as just an idea, when we would use the Rhein-Energiestadion, the soccer stadium of Cologne, to use it just as a heat storage, how long we can supply the city of Cologne. But before doing that calculation, we all sing together the hymn of the FC Köln. I wish you a lot of fun for that. Thank you very much.
The Rhein-Energie soccer stadium is 220 meters long, 180 meters wide, and 28 meters high, so it has a volume of 1,108,000 square meters. If we were to integrate a TES in the Cologne district heating system with this volume, it would have a thermal energy capacity of 77,000 megawatt hours. The actual power capacity of the Cologne DH system is 1,300 megawatts. A TES of this capacity will cover 60 full hours of the district heating network demand, or 10 days of normal operation for 70,000 houses. If we were to operate this TES in combination with the Cologne CHP plants, assuming a CHP rotation of 0.6, it would be possible to offer an electrical control power of 2,000 megawatts for about 60 full hours, which is comparable with the power capacity of 2 nuclear power plants.